So what else that we can learn from this problem? Well, when I have a look again at the time point for when the observer on the spacecraft can see the pulse emitted from the F point, it just happened to be a negative value. So I'm thinking, what if we can just then move on the time point here to the positive value, and how it can be different for the coordinates, for the position that the reference A, the person from the space station, can see. So then I try, right? Because what matters the most in all these kind of transformation is just the gap, right? As we always have the gap for like the distance based on what the people on the spacecraft see is like 2,000 meters, and the time is like 5.3 microsecond, then it should be fine, right? Okay, so instead of having TF as negative, I will set TF as 0, right? Because it occurs first before when they can see the signal from the R point. So then it just turned out that R point now will be plus 5.3 microsecond. And then for the X is also like still the same direction positive in this direction towards the right. So then at X prime F is still like 2,000 meters and X prime R still like 0. Now with these four variable, we can just like plug back into the Lorentz transformations again. With the V here is a negative value, because that will be how the space station seems to move compared to the spacecraft in the opposite direction towards the left. Okay, so here, there you are. And I really love doing this because I see, oh, this is really beautiful. Like I can just like see how Lorentz transformation really works. And we can see that just plug in those values here. X prime for the XR to be 0. Then the V here, negative values. Then the T here is as a TR, which is the positive values here. Plug it in. Then I found XR to be this much, right? It's like 2,000 something. Wow, so that's not 0 anymore. But could it be wrong? Let's see. Okay, then I continue with the TR and just plug in on these values here again. So I believe that you can also do it yourself too. So if you want, just pause the video and do it yourself and then just double check with me the result. What I found is that very interestingly and correctly, that XF, this value, it's just like greater than XR by the same amount of 1,200 meters. Then okay, I got things correctly, right? And also like for the time of the at the R and the time of the T, they should be like coincident with each other at the same value. So that's perfect. It just once again proves to me that Lorentz transformation really works and works very well. So after all, and after like much more exploration rather than just what the question asked, I try to visualize everything here. So don't be panicked to see many things going on here. We will work through these together, okay? So here first, for the person who stay on the space station, they see that the light pulse comes from the R position, the rear of the space station, and the front, the F, happen at the same time, simultaneously. And as we have said, we pick it to be like 0, time point. The length here is the proper length for the observer on the space station. See, it occurs right at the same reference and also like at the same time. You see that this is the proper length here, and then it will see that a spaceship coming, then it's coming here, and then later when it reach here at this point, then it just happened to be this is the same coordinate here, x0 here, okay, and it's after a time. So this is how do I know that this is the value, right? And this should be the value. So in order to figure it out, we need to have a look back at how the spaceship see the space station moving, okay? So again, for the space station observer, they will see that the spaceship is flying towards it at a very high speed, right? Like 0.8 times with the speed of light, that's the v, and it's going in this direction, right? And it will see the spaceship kind of shorter compared to the proper length of the spaceship. So if you stay on the spaceship, and I Google a little bit about what is the largest spaceship these days, and I found like the distance to be like 120 meter. So I try to scale it up to match with the length of the space station. You can see it's just like 1/10 of this one, and then we can see that it will seem to be like shorter if you stay at the space station because it travel at really high speed. Length contraction, remember that? That is length contraction. Okay, so again, how can I find these value? Have a look at this one here. For the person stay at the spaceship, we have an observer here, okay? He or she or they doesn't and don't see the pulses happen at the same time, but at two different time points. First, they will see that the pulse emitted from the F position at 2,000 meters away from the spaceship, okay? From an original that peaked at the spaceship. And also, it will happen at some time before, which is before the time when it sees the pulse at the R position by this much amount of time. So if this one is 0, this one is just like negative of minus 5.5 microsecond. Clear, right? And again, the space station length proper is this much. So the length proper should look shorter by that gamma factors. And that's why you can see that the space station just looks as if it's just 720 meters to the one on the spaceship. It's just shorter, okay? And then for the one on the spaceship, they will see that they stay still. They're not the one who moving, but to them, the one is moving is yes, that's right, it's the space station, right? And for the space station, it will move towards the left at the speed 0.8 of speed of light of c. So then you can see how far the spaceship can travel in that much of time. Yes, this will be this value. So if you try to plug in 5.3 microsecond here with the speed 0.8 of the speed of light, you will find this value. And then it all makes sense here because you know what? Then later when the spaceship arrives here after that much amount of time, this length is 720 meters plus with this value here, perfectly equal to 2,000 meters, where they can see the F position at the beginning. So then everything fall into places, right? Everything makes sense. And now if you compare here, you can see again about the length contraction rule again, also like time dilation. For the spaceship, it sees that the space station is moving at this much amount of time. This is the time the spaceship can, the one on the spaceship feel. But for the space station, see, because you see the ship moving, and the ship thought that, oh, I'm moving at just in like 5.3 microsecond. But for the people on the space station, they see differently. They see the time is longer. And how long is it? It's actually longer by that gamma factor, right? And that will be 8.8 microsecond. When you have like the gamma factors time with that 5.3 microsecond, you will find this value. Make sense, right? And again, because this is how long the people on the space station feel, so it also see that, oh, the spaceship had traveled that much distance. So that distance again is longer than how the spaceship see the space station travel. And by how much? By that just gamma factor again. So that's why you can see here, this one is longer And this is not like length contractions here that we're talking about, but it depends on the time dilation here. Time is dilated, and that's why the people on the space station see that the spaceship have traveled this far, further than the spaceship seeing. Okay, makes sense, right? So that's everything that can help us to understand about the length contraction and about the time dilation, right? And it's just this figure here is perfectly, you can see that there's not much difference, right? Yeah, because they the same. But what I try to highlight here is that if you pay attention to these values here, if this one is a negative, this one is a 0, then this is just like a shift in the way we do the measurement of the time, right? Like you can start the stopwatch at some point, but the time duration is just like the same. It's still like the same 8.8, it's still like the same like 5.3, but it's just the time point is different, okay? And because the time point is different, the coordinate also change along with it as well. So like for this one, you can see that instead of having the origin at the space station, now the origin of the space station is just like further left towards from it. So then we can see that the position of the R at the beginning is not starting with 0. But that doesn't matter because it's still the same thing. It's just how we describe it differently using different position for the origin. Okay? So I hope that everything is clear. And the key point is that you can see that we can have everything here with the Lorentz transformation. So stick with that in mind. I hope that it makes sense, right? Finally, with this kind of knowledge and practice, how can we apply to our problem? Because we need to earn the points in the end, right? So actually, after this much exploration, I could kind of confidence myself now that I can do this problem easily, and I hope that you can still feel the same. Because you can see that based on the equation, we can also like have a really quick version of it. Because you can basically say that if you got xf prime minus xr prime, it will just equals to like gamma as the common factors. Then you have like this is xf minus xr, right? And this one minus with the same common factor like v, and then you have this one is a t f minus t r. Okay, so just as long as you remember, you start with f first, then everything have to start with f first. That's it. And basically they just write it down simply like delta x prime. This is just like delta x, and this is just like delta t. You see that? So that's why they kind of have this kind of version of this equation, but they're basically the same. And then just plug in a value. I don't think that it could be difficult for us to do, because this one just like 0, then everything goes 0. Then just have this one left, and this is like 2000 meters as we did before. Then the same thing for the light as well. And when we see this one less than 0, then it just happened that this one should be less than this one, which means that F should happen first. So what's the conclusion? The conclusion is that just use the Lorentz transformation. Okay, that's the safest way to solve this kind of problem, because with length contraction and time dilation, you have to make sure that you can identify which is the proper one, okay? And when you work with the proper one, proper length especially, you have to make sure that that will be the difference in length between two positions, x2, x1, but the value have to be measured at the same time. That's why here the R happened at a different time. From the the light pulse emitted from the F position occur at a different time point from the one at the R. That's why we cannot apply the length contraction here.